Welcome to the Deep Dive, the only show that takes your overwhelming stack of sources and filters it down to the essential insights you need to be completely in the know. Today, we are strapping in for a dive into, well, the ultimate black box, the human mind, and how we are currently engineering ways to connect it directly to the digital world.
Indeed. And we're moving far past the theoretical here. We're examining brain-computer interfaces, BCI, not just as, say, medical devices, but really as catalysts for human augmentation.
Okay.
This merging of biology and engineering and the profound philosophical shifts it represents, well, it's encapsulated by the term technogenesis.
Technogenesis. Okay, let's unpack this immediately. Because when most people think BCI, they think science fiction, right? Or maybe a recent flashy tech launch. But our sources point out that the foundational concept, this idea of a direct communication channel between the brain and external devices, bypassing the usual nerves and muscles, that was actually conceived way back in 1973 by Jacques Vidal.
That's right, 1973. It's an old idea that's finally meeting technology advanced enough to, well, make it work.
So nearly half a century ago. Amazing.
It really is. And our mission today is pretty comprehensive. We need to move beyond just theory and grasp the exact technical components, the literal architecture of a BCI system.
Okay.
Then we'll review the, frankly, astonishing practical capabilities already achieved, from restoring communication to enhancing memory.
Right.
We'll also analyze the shifting global research leadership, who's leading and why. And finally, we absolutely have to confront the critical, ethical, and philosophical implications raised by this merging of human and machine.
And we should probably start with BCI's foundational success, the thing that provides that initial aha moment of real-world utility and restoration.
Exactly. That's where it proved its worth first.
This technology has already been essential for people who have lost traditional means of communication or control. People with severe neurological diseases like ALS, brainstem stroke, or even certain symptoms linked to schizophrenia.
Precisely. BCI has restored their ability to interact with the world. It's enabled them to control external devices, things like cursors, keyboards, wheelchairs, using only their thoughts. The clinical utility, well, it's not really in doubt anymore.
Powerful stuff.
But before we explore the, let's say, more enhancement-focused future, you, the listener, really need to understand the architecture that makes all this possible in the first place.
Right. Let's look under the hood, the plumbing of the system, so to speak. The typical BCI system works in a pretty clear linear flow. There are three fundamental components. It's kind of a closed loop. But for understanding it, breaking it down helps.
Yeah, we can visualize this as three sequential blocks. They have to work together flawlessly. Signal acquisition, signal processing, and the BCI application itself.
Okay, let's start at the source. Signal acquisition. This is where the brain signals, those tiny oscillating electrical voltages from billions of neurons firing, are actually captured.
That's our absolute starting point. We're capturing the raw electrophysiological signals that define the brain's neurophysiological states.
So like intent to move or seeing something.
Exactly. These signals encode everything from intended movement and vision to specific cognitive responses, like recognizing something familiar. Critically, these raw signals are incredibly faint and noisy.
Noisy how?
Well, you get interference from muscle movements, eye blinks, even electrical noise from the environment. So they must be filtered to remove these artifacts, then amplified, because they're so weak, finally digitized so the computer can actually process them.
Oh, right.
The performance of the entire BCI system, really from start to finish, it all hinges on the quality, the signal-to-noise ratio of what we acquire right here at this first step.
Okay, so if acquisition is gathering the raw material, then signal processing is where the magic happens, the engine room that refines that raw data into, well, conscious intent.
Yeah, that's a good way to put it. And it has three crucial substages. And yes, they sound very machine learning intensive because, well...
Okay, what's first?
First is feature extraction. Think of the raw electrical data like this huge, noisy lake of information. We don't need the whole lake. We just need the critical features, the specific ripples, let's say, that actually encode the user's intent.
So you're looking for specific signatures.
Exactly. We're isolating specific electrophysiological signatures. This might mean looking at time domain characteristics, like the amplitude or the timing, the latency of an event-related potential, or ERP.
Like the P300 you mentioned.
The classic example, yeah. The P300 component.
Yeah.
It's a positive spike in voltage that appears about 300 milliseconds after someone detects a target stimulus they were looking for.
Okay.
Or we might look at frequency domain features, things like sensoromotor rhythms or SMRs, which change when you plan or imagine a movement. or even the firing rates of individual neurons if you're using invasive methods.
So you have to figure out which Whipple the user is actually using consistently.
Precisely. You have to establish which of these features is reliably linked to the user's intention before you can even begin to design the decoder part.
Okay, so feature extraction finds what matters in the signal. Then feature classification figures out what that signal actually means.
Correct. This part uses sophisticated machine learning algorithms. Their job is to recognize patterns within those extracted features that consistently correspond to a specific desired action.
For example,
For instance, recognizing a specific pattern of SMR activity that reliably translates into the user thinking, move the robotic arm forward. Or maybe a P300 pattern that means select that letter.
got it. And the final step in processing.
Feature translation. This converts that classified, recognized pattern into an actual command for the external device.
So moving the cursor, changing the volume, typing a letter.
Exactly. That's where intent becomes output.
Yeah.
But there's a massive constraint here, a really important one. The algorithm needs adaptability
Why is that?
because the brain isn't static. It's constantly changing due to neuroplasticity. Learning, fatigue, even just time passing
Right.
changes how neurons fire. So the algorithms must continuously track these inevitable neural shifts over time.
So they still generate the right commands.
Exactly. They need to adapt to ensure they still produce accurate output. It's more like an ongoing dialogue between the user and the system, not just a one-time setup.
That makes sense. And the final piece of the puzzle is the BCI application itself, the external device being controlled. A mouse, wheelchair, robotic arm, you name it.
Right. That's the output stage.
But you mentioned an important distinction earlier. For certain restoration problems, like vision or hearing loss, the control signals might actually be sent back to the brain.
That's the key distinction for neuroprosthetics, yes. In those cases, the BCI doesn't just read the brain, it has to write back to it. It sends stimulation patterns, maybe to the visual cortex or auditory nerve. This completes the feedback loop needed for genuine functional restoration.
Fascinating. Now, the biggest technical divide, the one driving so much current research, seems to be how we do that initial signal acquisition. Invasive or non-invasive, we really need to spend time on the trade-offs here.
Oh, absolutely. The trade-offs are fundamental, and they pretty much dictate everything else.
So, invasive first, electrodes inside the head.
Right. Invasive BCIs. This means electrodes implanted either just onto the scalp, sitting on the brain surface, it's electrocorticography, or ECOG, or even going directly into the brain tissue itself using microelectrode arrays.
And the benefit.
Fantastically high-quality signals. You get an excellent signal-to-noise ratio because you're right next to the neurons firing. The benefit is precision. Much clearer data.
But the cost must be huge.
It is. Mandatory brain surgery, obviously. There's a risk of infection, inflammation, the body potentially rejecting the implant. And then there's the slow, inevitable degradation of signal quality over months or years as scar tissue forms around the electrodes. It's a major hurdle.
Okay, so that's invasive. What about the other side, non-invasive DCIs? Things like EEG caps with electrodes just placed on the scalp. No surgery sounds great for, mass adoption.
It definitely avoids the surgical risks, which is a huge plus. But, and it's a big but, they suffer from a major engineering problem: weak brain signals.
Why we?
The skull, the scalp, the cerebrospinal fluid, they all act as natural filters. They smear and dampen the electrical signals significantly before they reach the scalp electrodes.
So you got a poor signal-to-noise ratio.
Exactly. And that forces engineers to compensate. You need really expensive, sensitive amplification hardware. You need incredibly sophisticated, often power-hungry signal processing techniques just to figure out the user's basic intent from that noisy, faint signal.
So you trade signal clarity for convenience and safety.
That's the core trade-off: precision versus practicality, essentially.
Okay, to make this really practical for you listening, let's quickly survey the specific technologies researchers are actually using. We can group them by whether they record brain activity or stimulate it. Let's start with non-invasive recording tools. The workhorse seems to be EEG.
Electroencephalography, EEG, is definitely the most widespread. Why? Because it hits a kind of sweet spot. It's relatively inexpensive, it's portable, and critically, it has good temporal resolution.
Meaning it tells you when something happened very accurately.
Precisely. It's excellent for timing brain events. But the cost of that portability and affordability is low spatial resolution.
So you don't know where exactly the signal came from.
Right. It's like trying to pinpoint a single conversation in a huge, noisy stadium just by listening from the entrance. You know someone's talking,
Yep.
roughly when, but not precisely which seat.
Okay. Then you have FNIRS, functional near-infrared spectroscopy. That sounds like maybe a portable compromise.
It is, sort of. FNIRS measures brain activity indirectly. It looks at changes in blood flow and oxygenation, the hemodynamic response, similar to fMRI, but it uses near-infrared light shown through the skull.
Advantages.
It's portable, certainly more than an MRI machine. It's cheaper than fMRI. And it's less sensitive to electrical noise than EEG, which is helpful.
The drawback.
The major drawback is that it suffers from both low spatial resolution and low temporal resolution. The blood flow changes, the measures are inherently slow, so it gives you a kind of slow, blurry picture of the brain activity.
Got it. And then at the really high end, the big machines strictly confined to research labs, fMRI, and MEG.
Yeah, these represent the gold standard for resolution, but they come with massive limitations for BCI. fMRI, functional magnetic resonance imaging, provides excellent spatial resolution. It lets us pinpoint activity to very small brain regions, which is fantastic for detailed mapping.
But it's measuring blood flow again, so it's slow.
Right, its temporal resolution isn't great. MEG, magnetoencephalography, on the other hand, measures the tiny magnetic fields produced by neural currents. It provides excellent temporal resolution, much better than fMRI or FNIRS.
So what's the catch with MRI and MEG for BCI?
The reality check is they are massive, bulky, and incredibly expensive, millions of dollars. And MEG specifically requires a heavily magnetically shielded room to function at all, to block out the Earth's magnetic field and other interference.
So completely impractical for any kind of human augmentation outside a dedicated lab setting.
Absolutely impossible for everyday BCI use.
Okay, so the recording tech dictates the environment. Now, if we switch sides and look at non-invasive stimulation tools designed to actually change or enhance brain activity, what are the key players there?
Transcranial electrical stimulation, TES, is probably the most popular right now. It's cheap, it's portable, and it's considered low risk, at least for short exposures.
How does it work?
It's conceptually simple. You place electrodes on the scalp and pass a small, controlled electrical current through them. This current flows through the skull and brain tissue underneath, modulating neural excitability, making neurons slightly more or less likely to fire.
But you mentioned drawbacks earlier. Poor spatial resolution is still an issue, right? You're hitting broad areas.
Yes, traditionally TES has poor spatial focus, although newer techniques like high-definition TES are trying to improve that. But perhaps the bigger issue, especially for potential consumer products, is that massive consistency problem.
The non-responders.
Exactly. The source material highlights this. Because everyone's skull thickness, brain shape, and cortical folding is slightly different, the way the current flows varies wildly between individuals. Some people simply do not show the expected effects. They're non-responders.
Which makes reliable, standardized enhancement really difficult if it doesn't work the same way for everyone.
Very difficult. That heterogeneity is a huge challenge for translating TES from lab findings to real-world applications.
Okay. And the final non-invasive stimulation tech is transcranial magnetic stimulation, TMS.
Right. TMS uses a different principle. A coil is placed near the head, and it generates a brief, powerful magnetic field pulse. This magnetic field passes through the skull easily and induces electrical currents in the underlying cortical tissue, causing neurons to fire.
Benefits.
It has good temporal resolution. You can time the stimulation precisely. It's still quite bulky compared to TES. Its spatial focus is limited. TMS typically stimulates a minimum volume of about 1 cubic centimeter of brain tissue, just isn't super precise. And critically, it struggles to stimulate deep brain structures without inevitably stimulating all the shallower tissue above it as well. You can't easily target just a deep region.
Wow. So it really sounds like no single technology is perfect. Every system, whether it's recording or stimulating, invasive or non-invasive, is forced to make these fundamental trade-offs.
Absolutely. You're always balancing clarity, spatial, or temporal resolution against invasiveness and risk, against portability and cost.
And these constraints are precisely what push researchers toward the future, right? Finding clever ways to overcome these limits to actually augment our natural abilities.
Exactly. Which brings us nicely to how BCI is pushing boundaries far beyond just basic motor control restoration. Indeed, we're now exploring how BCI applications are moving into really fascinating territory. The most obvious next step beyond motor control is communication.
Okay, let's start with BCI spellers. You mentioned the P300 component earlier, that positive brainwave spike when you spot a target. The earliest systems use that to let people type, right?
That's right. That foundational work by Farwell and Donshin back in 1988 established the standard P300 speller. Usually it's a grid of letters, and rows or columns flash randomly. When the row or column with your target letter flashes, your brain produces a P300 response that the BCI detects.
Simple enough, but probably slow.
Traditionally, yes. To ensure the highest accuracy, you had to space out those flashes quite a bit, maybe a second or more apart, to prevent the ERP signals from overlapping and confusing the system.
But modern systems are faster.
Much faster. Modern BCIs are aggressively pursuing speed. They use very rapid presentation, often only 100 to 200 milliseconds between stimuli, trying to dramatically increase the information transfer rate, or ITR basically, how much information you can convey per minute.
But there must be a trade-off. Faster flashes mean more chance of errors.
Exactly. The ongoing challenge is balancing that accuracy with speed. Pushing the ITR too high can make the system less reliable.
And we see that speed jump dramatically when you move to invasive methods like ECOG.
Oh, absolutely. Electrocorticography-based systems, remember those electrodes placed directly on the surface of the brain, they bypass the skull issue entirely. They've achieved peak ITRs exceeding 100 bits per minute in some studies. That provides a much more fluid and natural communication experience than non-invasive methods can currently allow.
But the really cutting-edge stuff is moving beyond just typing text. You mentioned researchers are achieving speech synthesis directly from brain signals.
This is truly phenomenal work. BCI systems are learning to predict the intended speech information directly from the neural activity associated with planning the movements of the vocal tract, the lips, tongue, larynx, even if the person is paralyzed and can't actually make those movements.
So it's reading the brain's intention to speak.
Precisely. It decodes that intention and uses it to control a speech synthesizer device. Early attempts were, well, difficult, maybe achieving 70% accuracy for just a few vowel sounds.
But it's improving.
Substantially. By coupling the BCI decoding with sophisticated speech recognition technology on the output side, performance has improved dramatically. Some systems have reduced word error rates to as low as 25% for, say, a 10-word dictionary in real time. Still not perfect, but a massive leap forward.
If synthesizing intended speech is impressive, the breakthrough mentioned in the sources regarding high-performance brain-to-text by translating intended handwriting seems almost unbelievable.
That 2021 study in Nature was absolutely groundbreaking. They used implanted microelectrode arrays, those tiny needles in the cortex, to record neural activity while a participant merely attempted to handwrite letters in his mind.
Even though he was paralyzed and couldn't move his hand?
Exactly. The brain activity associated with the intention to form each letter was decoded directly into text on a screen. This method facilitated very high-performance communication, much faster throughput than typical grid-based spellers.
Incredible, but wasn't there a massive catch, something linking back to our earlier point about brain plasticity?
Yes, there was. Despite the impressive speed and accuracy, the system still required daily decoder retraining.
Every single day.
Every single day. The user's neural activity patterns associated with handwriting shifted slightly from day to day. So the user had to spend time each morning basically recalibrating the system, teaching it what his A signal looked like today, his B signal today, and so on.
That sounds incredibly inconvenient for practical daily use.
It's a huge barrier. This need for constant time-consuming recalibration remains a major obstacle for the practical, everyday adoption of these otherwise amazing high-performance invasive BCIs.
Okay, so communication is advancing rapidly despite challenges. But then there's brain-to-brain, B2B, communication. This really feels like we're stepping into science fiction linking two minds directly.
It does sound like sci-fi, but the concept, while still quite rudimentary, actually has concrete proof of concept, starting with animal studies.
I believe.
That's right. The initial success was demonstrated in rats. Researchers trained an encoder rat on a simple task, recording the specific pattern of its motor cortex synaptic activity while it performed the task.
Okay.
That specific activity pattern was then electronically transmitted and delivered into the brain of a second decoder rat via intracortical microstimulation.
And what happened?
Shockingly, the decoder rat, having received this template signal, was able to learn and execute the same task much, much faster than a naive rat that hadn't received the stimulation. It essentially transferred a learned skill, albeit a simple one.
Wow. And we're already seeing attempts to do this non-invasively in humans?
Absolutely. Non-invasive B2B collaboration has been achieved, typically using combinations of EEG to record signals from the sender and TMS to deliver stimulation to the receiver.
What kind of information can be sent?
Very simple stuff so far. For example, researchers successfully transmitted binary encoded words, essentially, a very basic form of telepathic communication from one person's brain to another's across the internet.
And I remember the source mentioning a collaborative game scenario.
Yes, the Tetris-like game. That was
Yeah.
clever. You had two separate human senders looking at the game screen. They used their thoughts, decoded by BCI, to send simple signals like rotate the block or don't rotate to a human receiver.
And the receiver.
The receiver, who couldn't see the game screen, processed the stimulation signal delivered via TMS, perhaps felt as a flash of light or a twitch, interpreted its meaning, and then manually executed the final action in the game.
So collaborative thought mediated directly by technology.
Exactly. Now, the information transfer rate is incredibly low, and the information itself is very simple binary choices. But it proves the principle. Collaborative cognition can be mediated directly by technology, potentially complementing or maybe even someday bypassing natural communication methods like speech or gesture.
Fascinating, if a little unsettling. Let's pivot now to memory and cognitive function more broadly. The sources talk about memory extension and enhancement, even developing a literal neuroprosthesis for memory.
This is incredibly sophisticated work. Researchers developed a neuroprosthesis based on a complex nonlinear systems approach, what they call a multiple input, multiple output, or MIMO model.
Okay, what does that mean in practice?
Think of it like creating a highly complex personalized translator. It monitors the patterns of neuron spike trains, the electrical firing of neurons as information flows between two crucial areas in the hippocampus, regions called CA3 and CA1.
And why those areas?
Because CA3 and CA1 are absolutely central to the brain's mechanism for consolidating short-term memories into stable long-term memories. It's a critical transition point.
So this device essentially watches the natural memory encoding process.
Yes, and if it detects that the signal transformations between CA3 and CA1 are degraded or incorrect, maybe due to brain injury, disease, or even just aging, it computes the correct transformation pattern based on its model.
And then
It uses precisely timed electrical stimulation to reinstate that correct pattern of neural activity, effectively bridging the gap and reinforcing or restoring the proper signal flow needed for memory formation.
So it's like a cognitive bridge. What were the results when they tested this in human trials?
Quite remarkable success, actually. They implemented this system in human subjects who were performing a standard delayed match-to-sample memory task. The results showed substantial improvements.
How substantial?
Short-term memory performance improved by an average of 37%, and long-term memory recall improved by 35%. This provides strong evidence for the potential of real-time manipulation of the memory encoding process to both restore and genuinely enhance mnemonic functions.
That really moves us into the broader territory of targeted augmentation using non-invasive stimulation, like TES, to actively change behavior and maybe even decision-making. We saw some pretty wild examples in the source material, particularly around risk-taking.
Yes, the ability of TES to modulate complex decision-making is profound and, frankly, a bit startling. The key studies targeted the dorsolateral prefrontal cortex, or DLPFC.
It's involved in executive function, right? Planning, impulse control.
Exactly. When TES was applied to the DLPFC, it drastically affected participants' risk-taking behavior in gambling tasks. Specifically, stimulation of the left DLPFC resulted in participants exhibiting significantly riskier behaviors.
And stimulating both sides.
Concurrent and nodal stimulation on one side and cathodal on the other actually diminished risk-taking overall compared to controls. So you can essentially tune a person's propensity for taking financial or physical risks just by applying a small current to a specific brain region.
That has enormous implications. And the problem-solving results are even more direct proof of cognitive enhancement, aren't they? Specifically with the remote associates test and that classic tricky 9-dot puzzle.
That 9-dot puzzle is the perfect illustration of enabling insight. The puzzle requires you to connect 9 dots arranged in a square using only 4 straight lines without lifting your pen. The trick is realizing you have to draw lines outside the perceived boundary of the square. Most people get stuck.
Right, thinking outside the box, literally.
Exactly. Studies demonstrated that applying TDCS, a form of TES, to certain prefrontal areas dramatically improved performance on insight problems like this. In one key study, TDCS enabled a remarkable 40% of participants to solve the difficult 9-dot puzzle.
Compared to how many without stimulation?
Compared to 0% in the control group who received sham or fake stimulation. 0%. This suggests the stimulation isn't just making people slightly faster or better at something they could already do. It seems to be actively enabling a shift in cognitive strategy, unlocking a novel problem-solving ability they couldn't access otherwise.
That's a powerful demonstration. Okay, let's shift our focus slightly now to how the brain works in highly demanding real-time environments. This brings us to passive BCIs and neuroergonomics. This isn't about actively controlling a device, is it? It's more about monitoring the state of the mind itself.
Correct. Traditional or active BCI requires conscious intent from the user. The user thinks move left, and the BCI tries to detect that and move the cursor left. A passive BCI, on the other hand, simply monitors the user's spontaneous brain activity in the background without requiring them to actively try to send a command.
And neuroergonomics.
Neuroergonomics is the discipline that studies the brain at work, particularly in everyday settings or complex, demanding operational environments. Think pilots, surgeons, air traffic controllers. Passive BCIs provide a crucial bridge between lab-based neuroscience and real-world neuroergonomics.
So what can passive BCIs detect?
They allow us to detect critical changes in cognitive states that affect performance. Things like decreased vigilance, meaning a drop in sustained attention over time, or periods of very high cognitive workload, perhaps when someone's working memory is overloaded.
And how do you detect that? What are the neural indicators that tell you a pilot or maybe an air traffic controller is reaching cognitive overload?
We typically look for specific changes in EEG rhythms or the characteristics of ERPs. The most consistent indicators of high mental workload or declining vigilance often involve an increase in theta brainwave activity, particularly in frontal areas, and a corresponding decrease in beta activity.
And this can be monitored in real time, outside the lab.
Yes, using portable, non-invasive EEG or maybe FNIR equipment, this allows for real-time tracking of cognitive state in operational environments.
This knowledge seems absolutely vital for maintaining simulation awareness, SA, in high-stakes jobs.
It is. Situation awareness is really the cornerstone of effective decision-making in complex, dynamic scenarios. It involves perceiving the elements in the environment, understanding their meaning, and projecting their status into the near future.
And BCI can help monitor SA.
Particularly Level 1 SA, which is the basic perception of critical cues in the environment. Studies have shown that a loss of SA, like missing a critical warning on a display, is correlated with specific patterns of coactivity in visual, prefrontal, and parietal brain regions. And importantly, these neural signatures of SA loss can often be detected extremely quickly.
How quickly?
Maybe 100 to 150 milliseconds after a critical event or warning change occurs, potentially even before the person is consciously aware they've missed something.
Wow. And if you can detect that loss of awareness or impending overload that quickly, you could potentially build adaptive interfaces that react automatically.
Exactly. That's the really exciting application here. It allows for a truly closed-loop human-machine system. You can use passive BCI monitoring of cognitive state, perhaps tracking the beta ratio we mentioned, to adapt the system or the interface in real time.
How would that work?
For example, if the system detects that an air traffic controller is under dangerously high workload stress, it could automatically simplify the information display, perhaps by filtering out non-critical data or highlighting only the most urgent alerts. The goal is to dynamically adjust the task demands to match the user's current cognitive capacity.
Resulting in better overall performance and safety.
Precisely. This shifts BCI from being just a communication or control tool into potentially a safety and performance optimization tool, seamlessly integrated into the work environment.
That's a really powerful idea. But all this explosive development, this incredible potential, it begs a serious question. Who is actually leading this revolution globally? And what are the practical barriers preventing you or me from buying a memory-enhancing helmet right now?
Yes. That takes us directly to the global research landscape and the, frankly, sobering reality of commercial viability.
Okay, so the sources included some pretty extensive bibliometric data looking at metadata from over 25,000 BCI publications. And the findings confirm what we've been discussing. This is a rapidly accelerating field.
Absolutely. The numbers show publications increasing roughly 1.5 times just between 2016 and 2021 alone. The growth curve is steep.
Exponential, really. But what's maybe more telling, or perhaps surprising to some listeners, is the dramatic shift in who is publishing. The analysis shows explosive growth in BCI publications coming out of China.
Yes, so much so that China actually surpassed the United States in terms of annual BCI publication output starting around 2019.
That is a genuinely tectonic shift in the global scientific landscape. What factors are driving China's incredibly rapid ascendancy in this field?
The sources strongly suggest this isn't accidental. It's a deliberate geopolitical and strategic move. China's exponential growth appears fueled by massive increases in government funding and focused institutional support.
Part of a larger plan.
It seems to align directly with the Made in China 2025 strategy. The explicit goal of that broader strategy is to achieve global technological leadership, aiming for superpower status by 2049. And neurotechnology, including BCI, is clearly viewed as a critical domain for securing that future.
So we're potentially seeing a shift from purely science-driven curiosity in some places to more state-driven geopolitical competition in others. Now, despite this recent surge from China, the U.S. still remains the overall leading country in total accumulated BCI publications, right? Because of its early start.
That's correct. The U.S. has the largest historical body of work. But that declining trend line in annual output since 2019 compared to China's sharp rise is a major indicator. It raises serious questions about future global research dominance, investment strategies, international collaboration, and so on.
It certainly does. Meanwhile, while the U.S. and China race ahead, the sources highlight a really serious concerning lag elsewhere, specifically in the global south.
Yes, the disparity is stark. Africa, for example, generates a remarkably low 0.95% of global BCI publications, less than 1%.
Less than 1%. Given the enormous potential for BCI in medical restoration, the stuff we discussed earlier for conditions like paralysis, that disparity seems incredibly troubling. Why is the African continent lagging so far behind in this area?
It really boils down to a resource issue, pure and simple. The sources attribute this tiny proportion primarily to insufficient research funding and inadequate access to the necessary technology and infrastructure.
It requires expensive gear.
Exactly. BCI research, especially at the cutting edge, requires very advanced, expensive, and specialized equipment, high-density EEG systems, powerful computers for signal processing, potentially neuroimaging facilities. These are often lacking.
And the human cost.
The humanitarian implications are significant. The sources note that Africa has over 80 million people living with disabilities, many of whom could potentially benefit tremendously from advances in BCI research and technology. This lack of local research capacity directly hinders progress toward achieving the third UN Sustainable Development Goal, which is focused on good health and well-being for all.
It's a stark reminder of global inequalities in science and tech access. Okay, so if the research is flourishing, at least in the global north and east, why aren't these BCI systems routinely available to us yet? Let's dive into those practical challenges, the roadblocks hindering commercial viability for mass adoption.
Right, because the potential is there, but the practical hurdles are still significant. The first major obstacle is simply cost and portability.
Still too expensive and clunky.
For the most part, yes. The sophisticated hardware and software required for reliable BCI decoding are often prohibitively high cost. Many systems are bulky, complex to set up and use, and currently really only suitable for controlled laboratory environments or maybe some specialized industrial settings.
So what's needed?
Before BCIs become commonplace consumer devices, we need radical improvements in developing cost-effective, user-friendly, and easily portable systems that an ordinary person could actually use safely and effectively at home or on the go.
Okay, cost and portability. What's next? You mentioned issues with implants earlier. That brings up the engineering nightmare of battery lifetime and implants.
This is a huge material science challenge, particularly for invasive systems. The brain is actually a surprisingly hostile environment for electronics.
How so?
Well, it's warm, it's wet, and the cerebrospinal fluid, CSF, that bathes the brain is basically a warm, salty solution. It acts as a surprisingly powerful solvent over time.
Corroding the implants?
Exactly. It corrodes the insulating materials around the electrodes and wires. This leads eventually to short circuits, signal degradation, failure of the device, and it significantly reduces the effective battery lifetime for any implanted BCI components.
So we need better materials or different power sources?
Both. There's desperate need for research into more robust, biocompatible materials that can withstand the brain environment long term, and also investigation into alternative power solutions, maybe harvesting energy from tiny micromovements inside the brain itself, or wireless power transfer to avoid implanted batteries altogether.
Makes sense. We also talked about the issue of brain plasticity earlier, the fact that brain signals change. That leads to the major practical problem of convenience and calibration.
This is arguably the biggest user interface killer right now, because the brain is constantly changing, adapting, learning that neuroplasticity we discussed, even the highest performance BCI systems, often require frequent decoder retraining and collection of new calibration data.
Like the handwriting system needing daily retraining.
Precisely. The user essentially has to dedicate time, sometimes every single day, just to teaching the system what their brain signals mean today. This makes using the BCI an active chore, a time-consuming hassle, rather than a seamless, intuitive extension of their body or mind.
So we need systems that adapt automatically.
That's the goal. Future studies really must focus on developing automatic self-calibration approaches, systems that can adapt to these natural stochastic neural changes in the background, without requiring constant, tedious user engagement for recalibration.
Okay, one more roadblock mentioned in the sources. It's a problem related to the structure of the research field itself. Multidisciplinarity gaps.
Yes, BCI is inherently profoundly multidisciplinary. It requires deep expertise from medicine, neuroscience, electrical engineering, computer science, data science, material science. The list goes on.
But some fields are missing.
Critically, some disciplines seem drastically underrepresented in the BCI research literature. For instance, the analysis found that only about 1% of BCI publications involve significant contributions from psychology, the discipline that specifically studies the human mind, behavior, cognition, and human factors.
Why is that gap so important?
It's crucial because without adequate input from psychology and human factors research, we risk developing technically brilliant BCI systems that are fundamentally unusable or impractical in the real world. We might build a device that decodes signals perfectly in the lab, but fails to account for cognitive load, user fatigue, learning curves, or how people actually behave and adapt outside controlled settings.
You end up with tech that works but nobody wants to or can actually use effectively.
Exactly. Bridging these disciplinary gaps is essential for moving BCI from the lab to meaningful everyday applications.
That makes perfect sense. Okay, so we have cutting-edge science pushing forward, but also significant technical hurdles around hardware longevity and user convenience. We're seeing global scientific leadership potentially shifting. Now, we absolutely must pivot to the really profound philosophical questions raised by this intimate merging of minds and machines. It challenges what it even means to be human.
Yes, because when we start to integrate the brain directly with machines in these ways, we fundamentally alter the nature of the human subject itself. This puts us squarely into the realm of philosophical discussions around posthumanism.
A concept championed by thinkers like N. Catherine Hales, I believe.
Exactly. Posthumanism aggressively challenges the traditional model of the human that has dominated Western thought for centuries.
And that traditional model, the one most of us are sort of implicitly raised on, is liberal humanism, right? The idea that defines the human subject primarily by things like individual autonomy, free will, rational consciousness, and self-determination.
Precisely. The sovereign individual. BCI integration and the ideas surrounding it seem to almost systematically dismantle those foundational assumptions.
How so?
Well, consider the persistent fantasy of uploading consciousness, the idea, advocated by figures like Hans Moravec and other transhumanists, that you could eventually copy your mind onto a computer hard drive and achieve digital immortality. Hales, among others, dismisses this as fundamentally flawed based on our understanding of biology.
And the core flaw lies in the embodiment argument, doesn't it? The brain isn't just software running on hardware.
Exactly. Human cognition, human consciousness is fundamentally embodied. We are not just abstract informational patterns. We are incredibly complex, messy, adaptive biological systems. Our current computational platforms, and likely any foreseeable ones, simply lack the astronomical complexity of the human neurosystem.
They miss crucial parts.
Critically, they fail to account for the absolutely essential role of the body itself, the endocrine system, hormonal regulation, gut microbiome. All these things constantly interact with and shape our mental processes. You cannot simply upload a consciousness because you cannot replicate the entire dynamic, embodied biological system that generates and sustains it in the first place.
That makes a lot of sense. This realization that we are tied to our biology and our tools leads us to the broader idea that humans have always been integrated with our technologies, the concept known as technogenesis.
Right. Technogenesis, drawing heavily on philosophers like Bernard Stiegler, suggests that humanity has always been in a state of coevolution with our technical environments. It's not that humans exist separately and then use tools. Rather, we invent tools, and those tools in turn shape us back. They change how we think, how we perceive, how our societies are structured.
So it's a feedback loop.
A continuous, recursive feedback loop. The coevolution of the human brain, sophisticated language, complex culture, and tool use is an ancient process, arguably dating back to the very origins of Homo sapiens. We made stone tools, and those tools changed our hands, our diets, our brains.
And this ongoing recursive relationship can be understood through something called the Baldwin effect.
Yes, the Baldwin effect is a concept from evolutionary biology that fits nicely here. It describes a dynamic where a species first adapts behaviorally to a new environmental pressure. Then, crucially, that species might actively change its environment in ways that actually favor and reinforce that initial adaptation, making it even more advantageous. This increases the selection pressure for traits supporting that adaptation.
How does that apply in the digital age with BCI and related tech?
In the context of modern technology and rapid change, this feedback loop manifests less through slow genetic changes over generations, and more through rapid ontogenetic changes, adaptations occurring after birth within an individual's lifetime.
Driven by brain plasticity.
Exactly. Our brains are incredibly plastic, especially early in life. As we constantly interact with our complex, engineered technological world, our brains physically adapt and rewire themselves in response to the demands and stimuli of that environment.
Which brings us directly to the phenomenon most listeners probably experience every single day. The so-called attention economy and the potential for neural rewiring. Our constant interaction with digital devices is systematically altering our brains, isn't it? Particularly in young, highly plastic infant and child brains.
Hales makes a very compelling argument here, identifying two crucial and perhaps competing forms of human attention. There's what she calls deep attention.
What's that?
Deep attention is characterized by a high tolerance for boredom, the ability for prolonged single-focus concentration. It's the kind of attention necessary for mastering complex skills, acquiring expert knowledge, engaging deeply with dense information like reading a 1,000-page novel or working through a complex scientific proof.
And the other kind?
The other is hyperattention. This mode is characterized by a low boredom threshold, a constant need for stimulation and gratification. It involves rapid scanning across multiple information streams, quickly identifying patterns, and getting a wide, shallow overview. Think channel surfing, scrolling through social media feeds, constant multitasking.
And the argument is that the environment we've built,
The ubiquitous digital environment we've created, smartphones, buzzing, endless notifications, algorithmically optimized feeds, creates a pervasive socio-technical landscape that systematically privileges and rewards hyperattention over deep attention.
so it shapes our brains to prefer that mode.
It creates a powerful feedback loop, exactly like the Baldwin effect, but on an ontogenetic timescale. Humans develop this adaptation hyperattention because the environment demands it, and then we actively reconfigure our technical environments, designing apps, interfaces, even future BCI systems, to cater to and further stimulate this mode, craving ever more intense informational stimuli and enabling rapid attentional switching.
We design the world that rewires our brains, and then our rewired brains demand we design the world that way.
It's a potent cycle. We co-evolve with the attentional demands of our technology.
Okay, if the machine is co-evolving with our neurology, reshaping our attention, where does that leave our traditional sense of individual control, of agency? The sources seem to argue that agency itself might be an illusion if viewed purely as residing within the individual. They suggest instead the idea of distributed agency.
This is a really radical philosophical conclusion, moving away from the liberal humanist subject entirely. As our technological systems and infrastructure become impossibly complex global networks, algorithmic trading, autonomous systems, human agency can no longer be seen as located solely within the individual human actor.
Where is it then?
It becomes distributed. Agency emerges from the complex interactions between human actors and increasingly sophisticated non-human or machinic entities within these vast technological ecosystems.
Can you give a concrete example of agency being distributed away from any single individual?
The global financial system is a prime example offered in the sources. It's an incredibly complex, adaptive technological ecosystem. Highly sophisticated algorithms, essentially machinic actors, make millisecond by millisecond trading decisions based on vast amounts of data.
With real-world consequences.
Massive consequences. Small perturbations or feedback loops within these non-human algorithmic systems can trigger cascading effects with catastrophic real-world impacts, as we witnessed vividly during the 2007-2008 global financial crisis. It becomes virtually impossible to pin the ultimate cause or responsibility for such events on any single human decision or intention. The agency was distributed across the network, the code, the human actors, all interacting in unpredictable ways.
That's a sobering thought. To really grasp this distributed nature and perhaps find common ground beyond the purely human, Hales's more recent research focuses on the vast, largely unexplored landscape of non-conscious cognition.
Yes, and this is a crucial distinction she makes. Non-conscious, which is different from the Freudian concept of the unconscious that deals with repressed thoughts or desires. Non-conscious cognition refers to the vast majority of information processing that happens below the threshold of conscious awareness.
How does she frame it?
Hales proposes a helpful tripartite framework. At the top, you have conscious and potentially unconscious awareness. This is a relatively small volume of our mental activity. Below that sits the massive realm of non-conscious cognition. And supporting both is the bottom layer of basic material processes, the biological substrate.
So the non-conscious is like the cognitive workhorse, the filtering system.
Precisely. The vast bulk of our mental life is non-conscious. It's not repressed. It's simply inaccessible to our conscious experience. Its primary jobs are absolutely vital. It supports conscious thought by filtering out the overwhelming, paralyzing flood of irrelevant sensory information, constantly bombarding us from the environment in our own bodies.
And it does more than just filter.
Well, yes. It rapidly recognizes complex patterns, draws inferences from incomplete data, handles automated skills and routines, all happening incredibly fast and efficiently, far beyond the processing capacity of our slow, serial conscious awareness. Consciousness has an extremely limited bandwidth compared to its powerful non-conscious counterparts.
And this realization that most of our cognitive processing is done by systems we don't consciously access or control, how does that connect back to posthumanism?
It further undermines the idea of the rational, autonomous, self-aware humanist subject being the entirety, or even the most important part, of cognition. It highlights the deep affinities and functional commonalities we share with other biological organisms, like animals, who also rely heavily on non-conscious processing. And perhaps even with sophisticated technical systems, AI, algorithms that also excel at non-conscious pattern recognition and inference. It dissolves the sharp boundary we like to draw around human uniqueness. And the deeper we dive into this coevolution, this distribution of agency, this reliance on non-conscious processes, the more urgently we absolutely must address the very real security, ethical, and societal consequences of integrating our most private cognitive processes with powerful network technology.
Right, because this level of integration, potentially connecting thought directly to the internet, it creates vulnerabilities on a scale we've never really faced before. Let's start with the immediate threats related to security and privacy.
It's a huge concern, and the technology is often moving faster than our ability to regulate it or even fully understand the risks. A major issue is the current lack of universal standards for BCI data handling.
Meaning applications can access raw brain signals?
Potentially, yes. Some applications might gain unrestricted access to raw brain signals. This creates a serious risk of extracting extremely sensitive personal information, not just intended commands, but potentially emotional states, cognitive biases, medical conditions, even subconscious thoughts, or proprietary knowledge, maybe without the user's explicit consent or even their conscious awareness.
Brain data is the ultimate private data.
It really is. And if these BCI systems are networked, communicating over the internet, the risk shifts from just passive data extraction to active malicious attack.
How so?
BCI internet communications create clear opportunities for cyber attackers to intercept or even intervene in the system. They could potentially alter the translated commands being sent from the user's brain to a device.
Causing real harm.
Absolutely.
Yeah.
Imagine altering the commands intended for a robotic arm, a wheelchair, or even a communication device, causing unintended actions with potentially disastrous physical or social consequences for the user. It's a terrifying prospect.
Are there technical solutions being explored?
Yes, researchers are investigating countermeasures. Advanced cryptographic techniques, secure hardware enclaves, and even technologies like blockchain are being explored as ways to secure the BCI data stream and verify the integrity of commands.
The source material outlined a hypothesized BCI functional model specifically designed to try and address these privacy and security risks. What did that architecture look like? How would it work?
It essentially proposed integrating several key protective blocks into the standard BCI pipeline we discussed earlier. First, engaging the user upfront with clear, predefined access rules before signal acquisition even begins, specifying exactly what data can be accessed and why.
Okay, user control first.
Second, incorporating a rigorous feature selection component within the signal processing block. The idea is to ensure that only the specific features necessary for the BCI's function are extracted and classified, discarding potentially sensitive but irrelevant neural information. Quality over quantity.
Minimizing the attack surface.
Exactly. And third, and perhaps most importantly for networked BCIs, adding an essential encryption block. All control commands transmitted from the BCI processing unit over a network to an external device would need to be securely encrypted.
Preventing eavesdropping or tampering.
Precisely. This encryption step is vital to prevent external actors from reading the user's intended commands, or, worse, injecting malicious commands into the stream.
Okay, so technical solutions are possible. But beyond the digital threats, the practical and physical dangers of invasive safety concerns for implanted devices remain a very sobering reality.
They do. The physical risks associated with implanting electrodes in the brain are persistent and significant. There's always the risk of infection during or after surgery. There's the risk of causing irreversible damage to delicate nerve cells or blood vessels during the implantation procedure itself.
And the body fighting back.
Yes. There's the issue of biocompatibility, the body's immune system potentially rejecting the foreign implant material. And even if it's initially accepted, as we noted before, the inevitable formation of scar tissue, a process called gliosis, around the electrodes is a major physical challenge.
Why is scar tissue so bad?
Because it acts as an electrical insulator. It gradually increases the impedance between the electrode and the neurons, degrading the quality of the acquired brain signals over time, and ultimately shortening the effective functional lifespan of the implanted device.
So lots of hurdles there. These technical and safety challenges feed directly into the much broader, overarching ethical, legal, and social concerns, ELSI, the society really needs to grapple with before we see widespread adoption of BCI, especially for enhancement.
Absolutely.
Yeah.
We face fundamental, currently unresolved questions. For instance, who is ultimately accountable if a BCI system malfunctions or causes unintended harm, whether due to a technical glitch, a cyber attack, or even just unpredictable biological variability?
And the user, the manufacturer, the doctor who implanted it.
Exactly. The lines of responsibility are incredibly blurry. Another question, does the technology truly guarantee long-term safety? We simply lack long-term data on the effects of chronic brain stimulation or indwelling electrodes over decades. What are the potential unforeseen consequences?
And the access issue.
And perhaps most pressingly, the question of equity. Does society ensure equal access to these potentially life-changing or performance-enhancing technologies? Or will BCIs only be available to the wealthy, further widening the existing cognitive, social, and economic gaps between the haves and the have-nots?
The neuro divide.
A potential narrow divide, yes.
And the specific problem of liability and agency seems dramatically amplified in those brain-to-brain communication scenarios we discussed earlier, where actions might be initiated by one person based on signals received directly from another person's brain.
It becomes incredibly complex. If a BCI system facilitates collaboration, or if the transfer involves complex information like memories or emotional states, which is still sci-fi but theoretically possible down the line, the traditional chain of command and responsibility completely breaks down.
How so?
If the decoder person initiates an action that causes harm, but they did so based on a faulty, misinterpreted, or even intentionally misleading signal sent from the encoder person's brain via the BCI link, determining legal or moral agency becomes a nightmare.
Who takes the blame?
Who is truly responsible? The encoder who originated the thought, the decoder who performed the action, the BCI manufacturer whose software might have glitched or been insecure. It challenges our fundamental legal and ethical frameworks for assigning responsibility.
Given all these profound risks and unresolved questions, the need for accelerated, thoughtful regulation seems absolutely paramount.
It is essential. We urgently need the development of universal technical standards, robust safety protocols, and clear ethical guidelines. We also need approval procedures from regulatory authorities like the FDA in the U.S., or similar bodies globally to be developed rapidly, ideally keeping pace with commercial interest and technological advancement.
We can't let the market run too far ahead of safety and ethics.
Exactly. Considering the incredible delicacy of the human brain and the potential for long-term, irreversible impacts from BCI technologies, rushing towards mass commercialization, especially for non-therapeutic enhancement applications, without robust regulatory oversight and broad societal discussion, would be highly irresponsible.
Okay, so lots to consider there. Let's try and bring this all together and conclude with a look at the future trajectory the 2040 forecast provided in the sources. How does this deep dive predict the technology might actually settle into our lives over the next, say, 2 decades?
The forecast presented is somewhat bifurcated, suggesting 2 different paths depending on the type of BCI application.
Okay, what's the first path?
For BCIs primarily dedicated to communication and control, basically, restoring or replacing lost sensory or motor functions for people with disabilities, the prediction is relatively optimistic. These are expected to become potentially routine elements of daily life by around 2040. Assuming, of course, that those significant technological barriers we discussed, particularly around cost, usability, reliability, and calibration convenience, are substantially overcome. If they are, we can expect to see significant improvements and wider adoption in areas like assistive communication, control of prosthetic limbs or wheelchairs, and maybe even novel applications like remote training or specialized personnel selection based on BCI aptitude.
Okay, so restoration and control look promising if the tech hurdles are cleared. But what about the enhancement applications? The ones based on neurostimulation like TES or TMS to boost memory or problem solving?
That's the second path, and the forecast there is much more cautious. These enhancement applications certainly look promising. They're marked as having strong potential field status in the roadmap terminology. But their future widespread adoption is considered much harder to predict with certainty.
Why the uncertainty?
The core safety and ethical issue remains a major question mark. The potential for unintended consequences. Facilitating or enhancing one specific cognitive function through stimulation might, unknowingly, come at the cost of impairing some other, perhaps unmeasured, function or cognitive capacity.
Trading one ability for another without realizing it.
Possibly. And critically, as we've mentioned, the long-term effects of chronic, repeated brain stimulation over years or decades are currently almost entirely unknown. The potential emergence of severe, unanticipated side effects down the road could quickly halt or reverse any trend towards massive expansion of these technologies into consumer markets for purely elective enhancement.
So routine restoration seems plausible by 2040, but routine enhancement is much less certain due to safety unknowns.
That seems to be the consensus projection, based on the current state of the science and the outstanding challenges. #TechOutro.
Well, this has been a truly monumental deep dive into a technology that feels both futuristic and, in some ways, already here. We've established that the technical components of BCI are surprisingly robust and continuously improving, even with those trade-offs. The philosophical implications, ideas like Technogenesis, posthumanism, distributed agency, they're genuinely restructuring our understanding of what it even means to be human in a technological world.
They absolutely force us to reconsider fundamental assumptions.
And we've seen the global research landscape is shifting rapidly, increasingly driven by intense national competition and strategic investment.
The geopolitical dimension is becoming undeniable. But perhaps the most crucial practical takeaway for you, the listener, remains that BCI benefits, as they stand today, seem to be highly individual dependent.
It's not like a uniform software upgrade for every brain.
Not at all.
Yeah.
Not everyone can effectively learn to control a BCI. This variability is sometimes referred to as BCI literacy or aptitude. Some people just naturally generate clearer, more decodable signals than others.
All right.
And similarly, individual responses to non-invasive stimulation techniques like TES show marked variability. We have the non-responders we talked about, and some studies even show that stimulation which helps one person might actually hinder performance in another, depending on their baseline abilities or brain state.
So it's inherently a personalized neural journey, not some standardized piece of hardware that works the same for everyone.
Exactly right. And this inherent variability in performance, both for control and for enhancement, brings us to the final, provocative thought for you to chew on.
Okay, let's hear it.
If our neuroscientific knowledge continues to advance, if we get better and better at relating specific, measurable patterns of brain activity or structure to complex personality traits, cognitive capacities, or behavioral tendencies, think things like risk-taking propensity, memory capacity, attentional control, learning speed. Then imagine a future where neuroscreening becomes a feasible, maybe even effective strategy for things like personnel selection.
You mean screening job candidates not just based on their resume, their past experience, or even their current performance on a test?
But screening them based on their brain's measured potential for performance, perhaps even their potential for augmented performance, when coupled with BCI, or a targeted neurostimulation device, designed to enhance the specific skills needed for that job.
Wow. So hiring based on neuropotential for enhancement.
What does that future mean for our fundamental concepts of fairness, merit, and accessibility in the job market? Who gets to decide which candidates have the right kind of brain profile? Who decides who is eligible, or perhaps even required, to undergo BCI augmentation for certain roles?
That is the deeply complex ethical and societal frontier we are already starting to approach. Determining who gets to be or is allowed to be a routinely enhanced posthuman and who is not.
Food for thought indeed.
It certainly is. Thank you for joining us for this deep dive. We'll see you next time.